just a minute. Let me set that up. Hopefully everyone can see that now. Welcome, and we'll go ahead and get rolling. So this is the off-grid systems webinar. A couple of caveats. First is, I am an employee of a distributor. I come from an engineering background. I'm not a code expert, and I'm not an attorney, and I am not a tax accountant or anything along those lines. So what we talk about today is best practices and so forth as best as we can. If you need specific professional advice, I recommend that you engage people who will charge you lots and lots of money for that, because that's what they do. And then if they give you bad advice, then you can charge them lots and lots of money in return. The other caveat is this is a 1-hour version of what is normally a full-day workshop. And the full-day workshop is a tightened-down version of what a lot of folks present as a week-long course. So there's a lot of material here. It's been pared down a bit, so I'm going to do my best to provide the most important and most basic level information. Plenty more to learn. We'll be offering an off-grid training, a 4-hour version later in September up in Portland as part of the OSIA event. So those of you in the Northwest might want to get registered and make your way down for that if this is an interesting topic for you. We'll be covering off-grid, and Outback will be down there covering battery backups. So you can come in person, get a little more detailed information. All right, all of that out of the way, we'll roll right into it because, as I said, there's a lot of material here. So we'll start off talking a little bit about batteries. So within the renewable energy space, we're usually talking about lead-acid batteries. For those of you that have interest in other batteries, missed the presentation on energy storage we did about a month ago. I think if you contact your TSM, maybe we'll download that information. I'm just going to focus on lead-acid batteries today because that's what 99% of these applications are using. Within that space, there's a couple of different types. So there's flooded batteries where you have literally the liquid electrolyte, which in this case is sulfuric acid, and it's just in the battery, and the plates are there suspended in the acid. And then you have what are called non-spillable valve-regulated lead-acid batteries, and these include gel type as well as absorbed glass mat or AGM. So in a gel battery, the electrolyte is actually a gel material, kind of like toothpaste or the stuff you find if you ever take apart a diaper. It's that kind of material, where an AGM is still a liquid electrolyte technically, although it's suspended in this sort of fiberglass type of material that holds it in place. And the idea with those is that you prevent the stratification that you get with flooded batteries. So the concentration of acid is the same all the way across the plates from top to bottom. That said, we'll kind of roll into different battery issues. So capacity, a number of things can impact the battery capacity. Most notably, the rate of discharge can impact battery capacity. So if you look at in the catalog or on a battery spec sheet, you'll find a number of ratings for battery capacity, and they'll be like 20-hour rating, 8-hour rating, 100-hour rating. So most of your battery manufacturers will typically put a nameplate on their battery that's the 100-hour rating. At AEE, we typically use the 20-hour rating, or in some cases the 24-hour rating, because that's the more common cycle in an off-grid system. So that's how we typically rate batteries and how we call them out in our descriptions. So if we assume 20-hour rating is 100% of capacity, you notice it drops off pretty fast as you discharge that battery with higher current. So if you discharge that battery at 1 hour, you're going to get just a little over half of its 20-hour capacity, because basically the battery chemistry, there's more inefficiencies, more heat generation, the higher the current load. It's analogous to I2R losses in cable. The other thing to know is batteries, as most typically flooded batteries will deliver less than total capacity when they're new. So a flooded battery can take up to 150 cycles or so before it's operating at its nominal capacity. Sealed batteries, your VRLAs, typically within a cycle or two are at 100%. So they're more or less, correct out of the box. But those flooded batteries, you do have to keep that in mind when you set up a new system. Also, batteries will self-discharge if they're stored in high temperature. And that's kind of interesting as a caveat to the chart you see on the right. Temperature impacts battery capacity pretty dramatically. So as it gets colder, there's less battery capacity available. That just has to do with as the temperature drops, the activity going on chemically in the battery is slowed down effectively. Whereas when it heats up, the battery is more chemically active, and as it gets hotter, you're going to get more self-discharge. You're also going to be harming the life of the battery. So, a battery that might last 5 years at 80 degrees Fahrenheit, might last 2 years at 100, right? So it's a pretty dramatic drop-off if you're not careful about battery temperature. Speaking of battery temperature, it's important to note that this is the temperature of the core of the battery. So this isn't necessarily ambient temperature. And for that reason, when you install battery temperature sensors and things like that, you want to make sure they're adhered to the case pretty well, or better yet, between a couple of batteries so that you're getting the true reading. When you wire batteries, they wire pretty much like modules. So when you put them in series, you're going to add the voltage, but the capacity is going to stay the same. So in this case, if you have two 12-volt, 220 amp hour batteries, you wire them in series, you have a 24-volt battery bank, but it's still at 220 amp hours. Conversely, if you wire the batteries in parallel, they'll still be at 12 volts, but now you'll have a 440 amp hour battery. When we talk about putting parallel strings in, most systems we recommend no more than 3 parallel strings. Reason for that is every time you have an additional parallel string, you increase the chances of having voltage mismatches, different wire resistances, things like that, that could cause those strings to interact poorly over time. Similar again to modules where you might have a lower power rating module in there, and you have sort of module mismatch losses. You get a similar effect with batteries. So you want to keep that in mind. Keep the number of parallel string connections low, and that's the best way to keep that under control. Of course, regardless of how many parallel connections you have, you want to make sure that all of your cables are the same length, same resistance, and so on. And we'll talk about a little bit later, some solutions to help ensure that. Batteries should be charged every time they're used. So your lead-acid batteries don't have any kind of memory effect or anything like that to worry about. However, they really don't like to be left in what's called a partial state of charge. So if you take that battery down 5% or 10%, even fairly small discharges, you want to get it back up to 100% as quickly as possible. Definitely, you don't want to leave it more than about a week. If you're going to store the batteries, outside of the system, then you should be charging them, typically every 6 weeks to 6 months, depending on the type of battery that it is. The other thing to note is that batteries, like virtually everything we work with, is not 100% efficient. So when you recharge a battery bank, you're going to have to put in somewhere between 5 and 20% more energy to compensate for just the losses involved in charging and discharging batteries. So those losses tend to be a bit higher for flooded batteries, a bit lower for AGMs and gels, but it's in that range, and it's something we need to compensate for. Also, as I mentioned, you should always temperature correct the charging. That goes back to our little chart showing the battery capacity temperature effects. There's also voltage temperature effects. So you want to make sure that you install your charge controller's remote temperature sensor on the batteries and make sure it's adhered well. The other thing to note with flooded batteries is every now and then you're going to have to overcharge them, like deliberately overcharge the battery. So you'll do that in a 48-volt system. That would be putting them at, like, 62 volts or something like that. What you're really doing there is you're boiling that electrolyte. And as I mentioned earlier, it's to get rid of stratification. So in a flooded battery, you can have different concentration of electrolyte from top to bottom. And by equalizing, what you're doing is you're mixing that electrolyte back up so that acid's the same concentration throughout the whole battery. You never, ever do that with a sealed battery, valve regulated acid battery. It will destroy the battery. They can't be overcharged in that way. So it's good to note the difference there. Most of your battery charge controllers include an equalized function. The better ones disable that function if you tell it that you have a VRLA type battery. You'll see different battery voltages in the system. This is kind of a handy chart. This is taken from the catalog in the battery section, and just gives you an idea of what you should expect to see, give or take, when you put a voltmeter on a battery system. So your nominal voltage, 12, 24, 48. If you're fully charged and it's at rest, it's going to be a little bit above what the nominal bank voltage is. That's normal. That's what you want to see. If it's essentially fully discharged and at rest, it's going to be a bit below. You don't want to see that too often, but it's still perfectly normal. If it's charging, you're going to see it go way above the nominal battery bank voltage, and that again is normal. So 48-volt battery bank, may charge at up to 60 volts DC, and that's normal. If you're equalizing, it's going to be above the charge voltage, right? That's where you're 3 volts in that 48-volt system for equalizing. That can be an issue if you have sealed batteries and you notice that the voltage is going above 60 volts on a 48-volt system, for example. A little alarm bell should be going off in your head, and you should be scrambling to shut things down because something's going horribly wrong. But for flooded batteries, that's an equalized charge, and that again is something you may be doing intentionally. Likewise, if it's under heavy load, if you're really loading these batteries down, it's going to pull the voltage down below the nominal. So even if it's fully charged, if you load that battery bank down, it's going to look like it's fully discharged, right? So it's important to know not only what the voltage is, what the temperature is, but also what kind of loads are on the system, right? Is the inverter drawing at maximum capacity? What's going on there? Those are important things you'll need to know when you do a battery checkup. Mention again, just it bears repeating, make sure you've got the temperature controller or your temperature sensor installed with your battery charge controller. That's very, very important. Also a very good idea to have a battery monitor, a little shunt in there that says this is the power going in and out of the batteries. So we offer a number of those. They typically go with some equipment or other. The FlexNet DC is a pretty common one with Outback. The Trimetric is a bit more multi-platform. I believe Schneider has a similar system. So you just want to keep track of your batteries with those types of shunts. And then you just want to check your voltages, or if flooded batteries, you can use specific gravity during a maintenance call just to make sure that things are what you expect them to be. That's usually the first sign that something's going wrong, is that you have different cell voltages or the like. Your depth of discharge is also going to impact your cycle life. So what you're looking at here is, I believe this is the Outback 200RE batteries, just as an example. So as you notice, as depth of discharge increases, your cycle life drops off pretty quickly. So most of your lead-acid batteries that are out there that we're using for what we call deep cycle applications and renewable energy systems are designed for 50% depth of discharge. A lot of those batteries in that backup mode can be used to 80%, and some of your flooded batteries and even a few of your really big AGM batteries can be designed for 80% depth of discharge, but you still have this life-shortening effect as you discharge the batteries deeper and deeper. And as I mentioned earlier, you never want to leave the batteries discharged for more than a handful of days. 1 to 2 days is probably fine. A week, you're starting to do some minor damage to the batteries, and you may not get them back to full capacity after that. What happens there is the electrodes, the plates will start to have a sulfur compound build up on them, and that'll effectively take that portion of the plate out of the chemistry, and so you'll lose that capacity in many cases permanently. Adding water, this is really for flooded batteries. You don't do this for sealed batteries, obviously. You want to make sure when you add water that it's after the battery has charged. So you don't want to add anything but water. You're typically using distilled water. You'll fill to, there's a maximum level indicator in most batteries. You want to make sure you don't overfill them. One of the more common mistakes people make is they'll fill the batteries when they're discharged, and then as they charge, what happens is that the volume of the electrolyte will increase just because of the way the specific gravity is different. That means you have more volume per mass, and you'll have acid everywhere, and that's no fun. So want to be careful. You'll only fill them when they're fully charged. If you have a situation where they've been discharged below, the water's gotten below the plates, you want to fill them just barely to cover the plates, charge them up, and then fill them the rest of the way. The single point watering systems are available for a couple of brands. Trojan's the one you see here. These aren't terribly expensive, it's a few $100, but it really does make it easier to keep those batteries watered, and you're not making such a mess when you do it with one of those. So I do recommend those when they're available. It's very helpful. Similarly, battery safety. For those that haven't done a lot of work with batteries, there is some special PPE that you're going to want to have at a minimum. Chemical-resistant gloves, some kind of goggles or face shield. I also recommend an acid-resistant apron or some other acid-resistant clothing, as well as steel-toed boots. Batteries are very heavy. You don't want to drop them on your toes. And so steel-toed boots are a good idea, and something that not everyone has unless they're used to this kind of thing. Also, of course, you want to keep any kind of flames or sparks or metal objects away from the batteries. So you want to make your tools should be insulated. No smoking near batteries. Again, no kind of spark initiation. Your flooded batteries especially, but also even your sealed batteries will outgas a certain amount of hydrogen, and hydrogen, as most people know, is pretty flammable. It's good eyebrow singeing stuff. So you want to make sure you keep that away, and also, there's a lot of electric potential in batteries, so you can have arcing and sparking if you're not careful. So any acid spills you end up with, baking soda is a great thing to have around to neutralize the acid, just like in high school chemistry. It'll bubble up a little bit, and then it'll be more or less neutral, and you can clean it up with a vacuum cleaner. You want to make sure any vent caps are securely in place, and again, this mostly applies to flooded batteries. And then you want to make sure you have proper ventilation, and again, that's especially important for flooded batteries. You're going to want to vent that to the outside so you don't have hydrogen buildup in the home, as that can cause problems. One other thing that comes up a lot is you'll see people mounting their inverter right over their big flooded lead acid battery bank. Think about that for a few minutes. You have hydrogen gassing up into your inverter. That's probably not a very safe thing to do. Most inverters aren't going to be generating sparks on a regular basis, but they can, and what would otherwise be a fairly innocuous event can suddenly become a nice little fireball. So you want to make sure you vent those batteries outside if they're flooded. It's a darn good idea. Periodically, you're going to want to make sure that they're back clean and dry. Again, check your vent caps, check all your connections. Loose connections will tend to corrode, so you want to keep an eye on that. Do also recommend terminal protector, especially if you're in environments like on the coast or places that have fairly high humidity. You'll see a lot more corrosion. So a little spray application and stuff, or some quick coat, which I believe we sell, just helps to keep that under control. And then, as we said, baking soda and water it's a great way to clean acid residue off the batteries. Battery storage, got to make sure they're in the right kind of place. Again, remember all those temperature effects on batteries. We want to make sure that, that they're kept in a temperature-controlled space, that everything's fine there. Basements, garages are fine. You see a lot of off-grid systems with a dedicated battery building, like a little tool shed. As long as it's reasonably well insulated and it's not going to get too hot or too cold, it's usually going to work fine. You also, of course, want to keep rain out of there. Needs to be ventilated. For flooded batteries, you may need active ventilation. For sealed batteries, you typically don't need much. Any ventilation that's going to be required for occupancy is typically going to be fine for a flooded or for a sealed battery. So you're typically fine in those cases in a garage or something, not a big deal. But you don't want to seal these things up. You can get buildups of hydrogen. That's no fun. You want to protect the terminals from from people, pets, falling objects. So the systems you see here either have doors. This one actually has a door that goes over it. This one has clear plexiglass covers, basically just to prevent people from accessing the cables or the batteries without specifically intending to do so. Also, if you're in places like the West Coast with sizing requirements, you may need to bolt the battery rack to the floor, that sort of thing. You want to make sure you've accommodated for that. And then also, think about additional breakers and switches that are either going to be code required or just helpful for safety. A good example, again, is on this integrated battery rack here. There's a string level switch. This isn't required by any code, but it's really handy when you're doing installation or servicing of that battery bank, because you can just turn that off, and then that string is isolated. So it's pretty helpful. So battery bank sizing, you're going to look at your daily energy consumption. You'll get all that into to amp hours, and then you'll take that times the number of days of autonomy that you want to have. So in most cases, you're going to be talking a couple of days of autonomy. If it's more than a couple of days, you want to look at probably getting a generator or some other backup power source, because it's going to be a lot cheaper than to keep multiplying the size of your battery bank. That said, having 2 or 3 days of autonomy actually can be pretty good from a design standpoint, because it'll essentially guarantee that your battery bank is oversized for normal use, and it'll last longer that way. So you'll divide that by the recommended depth of discharge for the battery, so 50%, 80%, etc. And then you'll multiply it by a temperature multiplier, assuming that the batteries are in a place that's not temperature controlled. So again, you want to keep those batteries right around 77 Fahrenheit, 80 Fahrenheit, no problem. You start going below that, you're going to need to add a little bit of capacity to compensate for the cold temperature effects on the batteries. So your required capacity over the unit battery capacity, that's going to give you the number of parallel strings you need. And then, of course, the voltage, system voltage is going to yield the batteries per string that you'll need. So if you have 12-volt batteries, but you need a 48-volt string, then obviously you're going to need 4 in series, as we talked about. One note on this particular kind of calculation is that it is very iterative. So you may need to do this 3 or 4 times, looking at different batteries and then calculating the cost. When I do systems like this, I typically put it all in a spreadsheet. Spreadsheets are really good for that sort of thing, and you can kind of keep changing the variables and look at what gives you the best bang for the buck. If you need help with it, give us a call. We've got guys that can do this stuff pretty well. So moving on to overall system sizing. Here's your basic off-grid system. You can find this diagram in the catalog. You have your PV array. If you have any other energy source, say a generator here, or wind turbine, or micro hydro, or what have you, that's typically going to come in this fashion. But your charge controllers run the array. That powers the bus to charge the batteries, as well as run the inverter. So it's a pretty basic system, but you do have to size it correctly. So to do that, you're going to need certain data from the customer. So the first and most important is what's the daily consumption? How much energy is this application going to consume every day? Does it change seasonally? All of these kinds of things, right? And you'll do this in most cases load by load. One thing that's very helpful is, especially for things like refrigerators and televisions and whatnot, you can go to Energy Star website, and if they're Energy Star appliances, which most of them are today, you can actually find the annual kilowatt-hour consumption. So if you divide that by 365, you actually have a fairly accurate estimate of what that appliance will use on a day-to-day basis. So that's really helpful to have there. You're also going to want to figure out the peak load in watts and what the voltage and so forth of it is for each of the loads. Mostly what you're looking for here is, in the U.S., things that run on 240, because not all of your battery-based inverters will output 240, and if you have a 240-volt load, that's going to drive you towards certain inverters or force you to include a transformer. So you're going to want to make sure you know if there's loads that require different voltages. Also, if you're outside the U.S., you may have the 240, 50 hertz grid. So you want to make sure you accommodate for that and get the right equipment to handle that. So days of autonomy, as we mentioned, if you're in a situation where you expect inclement weather for a certain period of time, and again, the trade-off here is, do you need additional battery bank, or do you need a small fuel generator or some other power source to get you through those times? And then finally, your solar resource. And remember, if you're going to be using this off-grid system during the winter, then you're going to want to make sure that you can handle the darkest part of the year. So typically what you look for is December solstice solar hours, which you can find on PV Watts or the NREL Red Book. So you do a Google search for either of those terms, you'll come up with that information, and it's fairly reliable. But there's also in the catalog in the back there's maps, and those are indicated for off-grid systems for the darkest months. So you want to make sure you're using the right solar resource. Your load analysis, like I said, once you go through all these loads, there's a worksheet in the catalog that you're welcome to photocopy and use. It works a bit like a tax form, so that can be a helpful way to go. Or of course, use a spreadsheet, whatever form makes sense for you. You just want to make sure you collect that information in a way that you understand. Also, you want to make sure you account for standby loads. So people talk about phantom loads. Not everyone understands exactly what they are, but basically it's when you have, for example, your television and it's turned off but it's still plugged in, chances are it's still consuming a certain amount of power to be in ready mode. You'll also have on your inverter side what's called a no-load draw or a standby load, and that's where sort of when the inverters there are ready to go, it's going to be consuming a few watts just to keep it in that condition. So you want to make sure you account for that as you size your array. So you're going to need a variety of system options that you'll have to figure out. So what type of battery? Do you want to use a flooded battery, a sealed battery, some other kind of battery? You want to think about, is it going to be maintained properly? Do you have to ship it somewhere special? Flooded batteries can't go by air, so there's all kinds of considerations there. Where are you going to put them? So lots of considerations there. What's the battery bank voltage going to be? The general rule of thumb with that is the higher the better. So most larger systems are going to be 48 volts. Where you might use a smaller system is typically if it's a very small system, say a couple kilowatts or something, you might do that at 24 volts. Or if you've got a DC system with mostly 12-volt loads, then you might want to do a 12-volt battery system. Just depends on your situation. Then you're going to look at your charge controller type. If you want a PWM or an MPPT charge controller. Generally, the PWM controllers are going to be less expensive, but they're going to require you to use a 36-cell module. Whereas your MPPT charge controllers can pretty much use any module you like. They have a wider voltage input range, and they're also quite a bit more effective at energy harvest. So you'll typically get 25–30% more harvested energy from a maximum power point tracking charge controller, like say your FN80 or your Midnight Classic or something along those lines. And then of course your module type, which is going to be driven largely by the choice of charge controller. Different sources if you're going to for charging the batteries. So we typically focus on PV modules. As our name implies, we're primarily about solar, but we do offer a number of off-grid wind turbines, which can be great for supplementing the solar, especially if you're in mountainous regions with a lot of wintertime wind. It can be pretty effective to put up a small little off-grid wind turbine just to keep the batteries charged at night. If you're in a site that allows for microhydro, there's some options for you there. That's not something we deal with, but we can certainly point you in the right direction. And then, of course, some kind of backup generator. If you're in a situation where you're expecting no wind or solar for a long period of time, it can be helpful to have one of those on hand, just so the batteries don't get completely drained. So the array sizing, as I mentioned before, you're going to size this according to sun hours on the darkest month of the year. You're not going to use the yearly average like you would for a grid tie system. That's just because you need to make sure you have enough resource that you don't leave your batteries partially charged throughout the winter, because that will damage the batteries. And again, that's where a generator can come in handy. If you can trade the sizing off. Maybe you're going to undersize the array slightly, but you're going to have a generator there in case the batteries don't get fully charged. Then you can run that generator maybe once a week just to make sure the batteries are topped off. So when you look at your PV array sizing, as I mentioned, you go to the Red Book or you go to PV watts. And you're going to look at, in the Red Book, you'll find, depending on your module tilt, you look at December, or generally what's the lowest number. And you'll see, okay, it's going to be somewhere between 1 to 2.5 with an average of 1.4. In most cases, if you use the average number for December, you're generally going to be fine. If you want to be really belt and suspenders, you can look at the minimum, which is a bit extreme, but there it is. And you can use either of those numbers will get you a decent result. If you use PV watts, it's typically going to give you the average. If you notice, this number is slightly different than the Red Book. And what they've done here is they've used a different weather station than the official Red Book weather station. This one, I believe, uses the airport weather station. So it's slightly different. Again, not enough to really hurt you. You're going to want to pad that a little bit anyway. But this is probably an easier way to find the data you're looking for. And this is the new version of PV watts, by the way. If you haven't checked it out, it's a lot nicer than the old one. So, and then of course in the catalog we have the solar resource maps for dark month, and you'll want to look at that. Again, sizing off-grid systems. You typically wouldn't use these for sizing grid tie systems, as it's not the annual average; it's the solstice week. Sizing worksheets, again, there's also these in the catalog, which can be helpful. I refer to this as the 1040 easy way to size your off-grid system. It does work pretty much like a tax form, and again, it's in that format just to make it easy to carry on a clipboard. But you can also put all of this into a spreadsheet and go through it that way. If you come to us for help, we're going to be asking for a lot of the original information anyway that was on the load worksheet. I may ask you for some of this as well if you know it. That'll just help you design that system. So then the array sizing will be slightly different depending whether you're using pulse width modulated charge controllers or MPPT. So for a PWM controller, you're going to take the daily consumption, so your daily loads in amp hours, multiply that by 1.2. Remember, that's that 20% extra you got to put back in the batteries. You'll divide that by the sun hours per day. That'll give you a current, basically, that you can then size your modules with. So there you would look at the peak current rating, the IMP on the module data sheet, and then you would basically add parallel strings until you got to the current that you needed. So in most cases, your PWM controllers are going to be 12 or 24 volts, so you're going to have 1 or 2 modules in each string. So that sizes pretty similarly to how you would size for any inverter in terms of stringing up your modules. And then you just put that together, wired up in series or parallel, depending on how you need to configure the array. Again, these are typically for smaller systems. For larger systems, you're going to jump to an MPPT controller. A couple of popular models shown here. You've got for 60-cell modules, it's got to be MPPT type, right? There really aren't a lot of cost-effective PWM controllers that can handle the voltage difference between a 60-cell module and either 24 or 12 volts. So brings you to one of these guys. The nice thing about these is they're pretty straightforward. Most of them, there's a voltage limit of about 150 volts, which means you're going to be using strings of 3. In some cases, for example, the Classic has higher voltage versions available, which in a few cases will let you use 4 per string, which you might want to do once in a while. So those are out there. But your charge controllers are current limited. So what we mean by that is if you have an 80 amp charge controller, that might give you almost 4 kilowatts for a 48 volt system, but it's only going to give you 2 kilowatts for a 24 volt system. So it does make a difference, your voltage there, because it's the current that controls that, not the power. So you want to make sure you take a look at that. Again, there's tables in the catalog that can be helpful to determine what controller you need for what size of array. Okay. And then, of course, it's pretty common to oversize the array just a little bit. As long as you've got the appropriate overcurrent protection and cable sizes in place, systems typically go up to about 20% over. For example, if it's for an 80 amp charge controller at 48 volts, you might be putting in 4 kilowatts of PV. That's pretty normal. Again, you just want to make sure you have the right overcurrent protection and wires to be able to handle that. And the reason that's helpful there is it gives you kind of broad shoulders, as it were. You get more consistent charging throughout the day. You might clip a little bit at the high end, but you're going to get more overall energy out of the system doing it that way. So next, you're going to need, as I mentioned, various circuit protection. So you've got to have essentially breakers between the PV array and the charge controller. You're also going to need them between the charge controller and the battery. So each string of modules, even if it's just one module, has to have some kind of circuit protection on it, and typically that's going to be a 15 amp breaker. And that breaker has to be rated for the maximum voltage of the controller. So typically you're going to be using 150 volt DC breakers. If you're using like a classic 250 or something, or like a Morningstar 600 volt charge controller, that means you're going to have to be using a 200 volt or a 600 volt breaker. So you want to keep that in mind as well, because those higher voltage breakers are more expensive. So all of your array circuits are going to be on a separate feeder. So what you can't do is you can't take all of your modules, your whole array. Like let's say you have 30 modules in an array. You can't take all of that to a single feed and have a bus and then put 2 80 amp charge controllers on there. That'll, among other things, completely defeat the MPPT tracking capability of the charge controllers. So what you would do there is you would take 15 modules into one controller and then 15 modules into another controller, and electrically those are completely separate arrays, and they're managed completely on their own by each charge controller. And then, of course, the output can be fed into a bus accordingly. So you're going to size your controller breakers accordingly. Your controller breaker disconnect will also serve as a battery breaker, so that can be helpful there. If you use a lot of Outback systems, they actually have a nice little GFDI breaker that manages several functions, and that's one of them. So some differences between battery-based and grid-tie inverters. Battery-based inverters tend to work harder, so that's why the efficiency is a little bit lower. They're building their own waveform from scratch. They're going from a much lower voltage input. However, they're not managing the power point tracking. That's all done by the charge controllers. And then, of course, on the output side, you see a lot more 120 volt battery inverters. However, there are a lot of really good options for 240 volt these days, whereas almost all of your grid-tie string inverters are going to be 240 volt output. To size your inverter, you want to be looking at the maximum AC load. So you take all the loads, all the peak loads that you may run together, and calculate the sum of that. That's going to be basically your inverter size, your minimum inverter size. You're also going to look at any kind of startup loads or surge current draws. So think here any kind of motor, compressor, big things with big coils. So you want to take a look at those. You may need to size up the inverter. Most of your battery-based inverters will have an additional surge capacity. So the Radian, for example, it's an 8 kilowatt inverter, but it'll handle up to 12 or 16 kilowatts. It's in surge mode for a very limited amount of time, for a couple of seconds or maybe a minute, depending on how far over you are. You're also, again, going to look at, do you need a 240 volt inverter output and or transformer, or was 120 good enough? And then, of course, you're going to want to look at the no load draw of the inverter. If you have a generator in the system, that's going to drive you to certain inverter choices. Typically, if you have a generator, you're going to want to lean toward a 240 volt output inverter, like say a Radian or an XW or something along those lines that's made to take a generator. If it'll connect to the utility grid, you have to make sure the inverter is properly listed and rated for grid intertie. That means it meets UL 1741 for grid intertie operation. And most battery inverters will not mount outdoors, so you want to beware if you have a requirement for that you get a sealed inverter, and it may require you to do various other gymnastics with the integration. But just be aware that outdoors can be a problem for battery-based inverters, mostly because outdoors is a problem for batteries. So you typically got to put the whole system in one building. And then, of course, if you need modified sine wave inverters, can be a little cheaper, or modified square wave is more technically called. Not a good idea if you have stereos or laser printers or things that are sensitive to the power waveform. Various integration hardware is available. Lots of different stuff that you need here. I'm not going to go into a lot of detail just because, frankly, I'm running out of time. But conveniently, a lot of manufacturers now offer power systems. AE's actually built power systems like this for a long time, and a lot of manufacturers now provide them direct from the factory this way. So that's going to include inverters, controllers, battery monitors, various integration hardware, et cetera, et cetera. The nice thing about these is they're typically ETL marked as a complete assembly, right? So instead of having to check everything inside these boxes, the inspector really just has to look at your connection from the batteries to the inverter, and then from the inverter out to your load distribution. So it saves you a lot of time in inspection, as well as assembling the stuff on site. System controller is also a good idea. So there's the Mate, which works with Outback gear. There's analogous controller for the Schneider systems. And these just basically keep track of all the parameters, allow you to program the various inverters and so forth. They also, in some cases, will allow remote monitoring over the internet. So the current Mate 3, for example, comes with an optics package, which is Outback's proprietary monitoring system. And that's on par with most of what you see with a grid tie string inverter. So very helpful stuff. So moving into the last bit here, just want to stress with off-grid systems in particular, it's really, really important to communicate with your customer. They need to understand what are the limitations of the system, what do they have to do, what's covered under warranty, what's covered under service agreements, and then what happens if they push the big shiny red button you told them not to push. So what happens if they do something that they're not supposed to do, just so they understand what the consequences are. If you don't explain these things up front, they will come back to haunt you, because as I'm sure most of you have found, it's all your fault. You installed the system, it's all your fault. And it's doubly true for off-grid systems, because it's one thing when you have a grid tie system that's not working and someone's paying a little more on their electric bill. It's something else entirely when an off-grid system isn't working and someone has no electricity whatsoever, until you get out there to fix it. So the stakes are a little higher. The communication's a lot more important. For that reason, I typically recommend some kind of maintenance agreement. I call this getting paid for the work you have to do anyway. So when you sell one of these systems, it's a great idea to say, hey, you know, I sell this, you know, it comes with a maintenance agreement, and you either charge for that up front, or you negotiate a deal where they pay you so much a year to keep the system up. It sets the expectations, make sure, again, you're getting paid to make the drive out there, and most importantly, ensures that the system is properly maintained. So it'll keep working like it's supposed to work. And I recommend this for any kind of battery system, whether it's off-grid or battery backup. It's just a good idea. You're going to want to include in that online monitoring if you can get it, preferably one that can send you alarms and tell you when something's changing or going wrong, and then some kind of a site visit. So if you got sealed batteries, you probably only need to do it once or twice a year. If you're flooded batteries, you should be out there about every 3 months or so. Make sure the array is clean just like you would for grid-tie systems. Do an overall system checkup. If it's a backup system, for example, test it. And then sit down and chat with the user. Hey, are you going to buy an EV? You're going to do, our load's changing. Is Junior going off to college? Whatever the case. So that's basically the presentation. So we'll open it up for questions now.
All right, great. Thanks, Paul. Just a reminder to everyone, you can submit your questions through that questions pane, and we'll do our best to answer them. Also, just a quick note, the survey will pop up in a new window after you close out of the webinar. Please just give us a couple minutes and a few notes of feedback, and I'll send you a copy of this presentation for future reference. All right, and we'll get started with some questions here, Paul. First question. Are there any microinverter systems meant to use batteries as their power source rather than a grid connection?
So you can AC couple N-phase inverters with the Outback Radian. That's something that's been blessed by both manufacturers. Beyond that, I am aware of an inverter by Darfon. That's technically an off-grid microinverter. However, I still haven't figured out how they intend for you to build it into a system because it doesn't really draw from a battery. It draws directly from the module and just outputs whatever it's got. So would be fine for running a little fan or something, probably not something you want to build a system with.
Okay, great. We'll move on to our next question. Could you explain the difference in lifetime of an AGM battery versus the flooded?
So the big difference with AGM versus flooded, AGM is typically the sealed battery is zero maintenance. Whereas a flooded battery, you can replace the electrolyte. So you can get flooded batteries to last a pretty long time if you maintain them correctly. In real life, with most customers, a lot of them are going to be better off with an AGM battery because they're not going to put water in it, they're not going to equalize it, they're not going to do the stuff you got to do to keep that flooded battery going. On the other hand, if you've got someone who's really dedicated to living off-grid and really interested in that battery system and wants to monkey with it all the time, they can stretch that thing out. I've seen flooded batteries go for 15, 20 years if they're carefully maintained. But the big thing is, what's the customer behavior and how is that going to impact the life of the battery system?
All right, our next question here. Have many installers been required to meet the new code rule of rapid disconnect? Is there a solution?
So there really isn't a solution today for battery systems. There's quite a lot more involved in shutting down a battery system because obviously it's designed to keep providing power when everything else is shut down. There's a lot of work being done by the usual suspects. I know Midnight's working on a lot of things, as is Outback. Nothing's hit the market yet. So far, we haven't seen more than a couple of these systems, even get asked by the inspector about rapid shutdown. We are certainly starting to see it for grid-tie systems in mostly Maryland and Colorado, as far as I've seen. it's coming. I mean, make no mistake. We don't have the solutions, as products today, but they'll be here preferably, or hopefully in Q1 next year. We'll start to see some stuff on the market that can handle that.
Okay. Our next question. Let's see. There used to be desulfator for flooded batteries. Are they? Is that still in the market?
I think you can still buy them. We stopped carrying them because when we did some testing and some research, we found that they really didn't do anything. It was a bit of a snake oil deal. Basically, what a desulfator tries to do is pulse the plates to knock the sulfate off of the plate. It just doesn't work well. The battery manufacturers aren't very fond of them. If you have sulfation, your best bet is just to equalize the battery. If it's a flooded battery, if it's sealed, there's really nothing you can do. If it's a flooded battery, you just equalize it and then put it in float for a couple of days. That'll let you recover as much as you're going to recover. The sulfator, you're welcome to try it. Just be careful. You may be voiding the manufacturer warranty on the battery by doing that.
All right, next question. Please explain the purpose of a shunt.
So the shunt is for monitoring the energy going in and out of the batteries. So it's basically a kilowatt-hour meter for batteries. They use a shunt, which to measure the current, and then it just measures that current over time and calculates the kilowatt hours, if you will, or the amp hours that are going into and out of the battery bank. So when I refer to a shunt, like the flex on DC or something like that, it's really just a current meter is what we're talking about.
All right, great. The next question we have, what type of venting or enclosures are typically required for AGM and flooded batteries?
So AGM, it's pretty much just a shelf that's got just normal venting, like in, for example, the IBR, for outbacks batteries is just kind of open in the back, so it just has natural venting that way. It's just not completely enclosed. For flooded batteries, you typically would enclose those in something and then have either a chimney or an active fan venting those batteries. If you use a fan, you have to make sure that it's a sparkless fan for obvious reasons. You don't want to have a flamethrower. But yeah, I've never seen anyone require active venting on a sealed battery system. They just don't outgas that much. They're designed to not outgas. So you'll get a little bit, but not usually enough that it requires any kind of active ventilation. Where you need the active ventilation is also in high temperature areas. So if you're storing flooded batteries in the tropics, for example, some kind of active ventilation is probably going to be appropriate.
Okay, and we'll move on to our final question. Do you recommend nickel-iron batteries?
Depends. I mean, if someone really wants that long life system, those nickel-iron batteries can go for a good long time. There's a number of caveats to using them. You have to make sure that your inverter is programmed correctly because the voltage tends to drop off a little faster with nickel iron. We don't sell them. We get inquiries every now and then. Until pretty recently, the only nickel iron batteries available were coming out of China, so it was just really tough to get them. And then you got them, and then the quality was really kind of iffy. A lot of the manufacturers have cleaned up their act, and there's good stuff out there now. But again, it's just one of those things where these things are massive, they're incredibly expensive, and there's just not a lot of demand for it. I wouldn't discourage someone from using them, but at the same time, it's not the go-to choice for most folks, just because of the hassle of acquiring them and putting them in place. I mean, they're even more heavy and bulky than lead-acid batteries, and they're almost 10x the price.
All right. Well, that'll finish our Q&A session here. If you do have any further questions that weren't answered, feel free to email them to the email address on the screen, support@aeesolar.com. Or you can email them to myself, and I can direct them to the appropriate person. Thank you so much, Paul, for the presentation. Our next presentation comes in 2 weeks from today, and it'll be optimizing your sales success. so don't forget to register for that one ahead of time. You can also visit our website, aeesolar.com, and click on the events and training to find out new opportunities. As Paul mentioned earlier, we have some workshops coming up and some other training opportunities, so stay tuned for those. Paul, would you like to make any final comments?
Oh, thanks for joining us today. I hope everyone has a fantastic holiday weekend. Wish you all well, and have a good time, and don't get hurt.
All right, thanks, Paul. And don't forget, everyone, we have that survey that will pop up in a new screen after you end the webinar. Please take a moment to give us your feedback, and I'll email you a copy of this presentation later in the afternoon. All right, thanks again, everyone. Have a great weekend.